Okay, Assalamu alaikum. Today's tutorial will be short because we will only have two problems, one left from last tutorial and one with solving a problem. Okay, using Navier-Stokes equation to find the pressure field. Okay, because still you haven't solved problems with Dr. Khalid. Okay. Next lecture, inshallah, you will continue that. So our first problem is the same one from example 8.1, okay? But I want you now to find the volume flow rate using the stream function, okay? And compare it with the method or with the integral approach, okay? To find the volume flow rate. So for now, okay, we have the velocity in the Z direction. Okay, this is the Z direction in the 2D axisymmetric flow. This is the radial direction. Okay, and the theta direction will be inside the page. Okay, like this, it's rotating. So UZ, okay, which is a function of R only, it's U maximum 1 minus R squared over the radius of the pipe squared, which is equal to 6 1 minus R squared over the radius of the pipe is 0.02, okay, squared. That's it. So how to find the stream function? Okay, look here, axisymmetric flow. This is axisymmetric problem. Okay, I've told you what's the difference between cylindrical coordinates for 2D and for the axisymmetrical. Okay, this one, when you have a flow inside a pipe and it's like this, okay, it's not the same one as the one you solved in the slides, because the one you solved in the slides had a flow between parallel plates, which was a Coulter flow. Okay, this one is when the flow is in the Z direction and in the radial direction. So you have only those two directions, and the theta direction is inside the plate. But when you have something like this, like polar coordinates, okay, so you have the theta direction, okay, and you have the radial direction, and the Z direction is inside the plate. Okay, so our case is an axisymmetric case. Now, minus 1 over or 1 over R, we will use this one, partial psi by partial R is equal to UZ, which is 6 1 minus R squared over 0.02 squared. Now multiply R on both sides, so I will take this R outside, or I will cancel it, and this will be R and this will be R cubed. Yes? And now integrate with respect to R, so psi will be equal to 6 R squared over 2 minus R to the power 4 over 4 multiplied by 0.02 squared, okay, plus a function of R, yes, or a function of Z, because we integrated with respect to R. So what's left for us is to complete the stream function definition and find this constant f of z. So to find this f of z, we will use the second component, okay, velocity component, which is ur. It is equal to 0, as I told you, because if you can see from the problem here, okay, the flow is in this direction, so we don't have any flow of velocity in the radial direction, okay, it's only in the z direction. So equal to 0, which is equal to minus 1 over r, partial derivative of psi by partial z, okay. What's the derivative of psi with respect to z? This one doesn't include z, so the derivative will be 0, this term, look at it, and this will be f prime of z. So it is 1 over r, or minus 1 over r, f prime of z. And we can cancel the r because the other side is 0, so r multiplied by r, or multiply the 0 by r, it will be 0, f prime of z. This leads us to the fact that f of z is a constant. Okay, the function of z is a constant here. So we now generated an expression for the stream function, which is this one. And now we can find the volume flow rate. Okay, so the volume flow rate per unit width will be equal to psi 1 or psi 2 minus psi 1. Okay, the difference between the psi's. And psi 1 will be taken in this mid line of the pipe. Okay, because this is the pipe, it's going like this. Yeah, and this is okay. Like, let me draw a 3D. Okay, so the flow is in this direction. Okay, if you looked at it in 3D, you will find something like this. Okay, we call it, I don't know how to describe this shape. Okay, but it is as if you have a function of the second degree and you rotated it. Okay, so we want to find the volume flow rate. This will be our psi naught. Okay, and this is psi 1. We can either take psi 1 at the lower end or at the upper end, doesn't matter. So psi 1 will be 0, because if we substitute here 0 and here 0, r0, r0, it will be 0, and we will only be left off with c. So it doesn't matter what c we take. It's just like the slide problem. It doesn't matter what c we take, because either way c is going to be cancelled. We have here psi 2 and psi 1, and this one will include c, and this one will include c, so the c will cancel. So just for convenience, they tell you that c is equal to 0. Take c to be equal to 0. But it doesn't matter. Whatever the value of c was, it will be get cancelled. So psi 2, which is 6, r squared, I will substitute it 0.02 because it's at the pipe end over 2, or the pipe wall, 0.02 to the power 4 over 4 multiplied by 0.02 squared minus psi 1, which is at the center of the pipe. So here's 0, here's 0, and plus 0. So now we have find the volumetric flow rate, which is, let us substitute it, 6, 0.02 to minus 0.02 to the power 4 over 4 times 0.02 squared. Okay. 6, 0.02 squared over 2 minus 0.02 to the power 4 over 4 times 0.02 squared. Okay, is equal to 6 times 10 to the power minus 4 meter squared, okay, per second. Okay, this is the volume flow rate per unit width. And just remember something, that the width in the Cartesian coordinates represent the z direction, yeah, inside the page. But here, because we have a cylindrical coordinates, okay, axisymmetric flow, the depth, as I told you in the beginning, inside the page, it is theta. Theta is the one that's going inside the page. So, okay, and because theta doesn't have a unit, so it will be meter cube per seconds, okay? And this width will represent the theta, which is in this case 2 pi. So find the total volume flow rate, okay? The total volume flow rate, which is V dot, is going to be 6 times 10 to the power minus 4 multiplied by 2 pi. So 2 pi times 6 times 10 to the power minus 4 it is 3.77 times 10 to the power minus 3 meters per second. Okay, so that's how we find the volume flow rate from psi. It's just psi2 minus psi1. Okay, and tells you that take psi1 in the center of the pipe. Okay, and now the width will represent 2 pi. Okay, so just remember this number. Let's do it in the method that we know. Okay, that you know from before in fluid mechanics. So V dot is equal to integration of V d area, okay, the velocity d area. And now integration of U max 1 minus R squared over R capital squared, which is a constant. Okay, d area, I will change the d area to 2 pi R dr. Yes, so 2 pi R dr from 0 to R, which is equal to, take all the constants outside, which are 2 pi U maximum integral from 0 to R of R, here multiply R by 1, minus R cubed, multiply the R squared by the R, over 0.02 squared. Okay, and this one is U maximum is 6. Okay, and our R here is equal to 0.02. So do the integration and you will end up at the end with integration with bounds, or a bounded integral. Okay, x cubed over 0.02 squared. So the answer is 3.77 times 10 to the power minus 3 meter cubed per seconds. Okay, it's the same answer, same thing as if you do it using the integral approach or the integration equation, or if you do it using the stream function. Okay, so I just wanted to show you a problem in cylindrical coordinates where the width represents the theta. Okay, so if you have maybe a flow like this, okay, I don't know, maybe if the pipe is like that, it's somehow open, so it will be theta only. Okay, there's a problem also, it's a cylindrical one. Okay, cylindrical one. Okay, but you have a flow here inside the wedge. Okay, this is the wedge. Okay, and the flow is in this direction, so it is only in the radial direction. Okay, and now your width will represent the z direction. Okay, the direction that's not there, the z. So it is inside the page here. The direction that's not there is the theta. So yeah, that's it. Now let us solve the second question. Okay.